All right, well, good morning, everyone, and welcome to the State of Utah Energy Storage Summer Webinar Series. This six-part series will be held on Wednesday mornings from July 8th through August 12th, 2020. Just so everyone is aware, this session is being recorded and will be shared after the series concludes. The Energy Storage Summer Webinar Series is presented by the DOE Office of Electricity Energy Storage Program in collaboration with the Utah Governor's Office of Energy Development, Sandia National Laboratory, Pacific Northwest National Laboratories, Mustang Prairie Energy, Quintana Technology, and the University of Utah's Utah Smart Energy Laboratory. A couple of housekeeping items for today. We ask that all questions be held until the end of the webinar, where we will have a question and answer and discussion session starting at 12:20. If you have questions, I ask that you hold them until that time or send me your questions through a private chat message to Kevin Brooks. With that, I also ask that everyone remain muted throughout the session and use the hand raise function if you need to ask a question during that time. With that now, we will dive into our July 8th, 2020 webinar covering energy storage introductions and overviews. We will have an introduction to the series by Rob Simmons, OED Executive Director for the Governor's Office of Energy Development and Governor's Energy Advisor. Then we'll have an intro to energy storage and question and answer with Dr. Gyuk, Director of DOE's Office of Electricity Energy Storage Programs. Next, we will have an energy storage systems overview provided by Dr. Howard Passell from Sandia National Laboratories. And then lastly, we will conclude the webinar with the energy storage policy overview presented by Will McNamara from Sandia National Laboratories. With that, I would like to introduce our opening speaker today. Rob Simmons is Governor Herbert's Energy Advisor and the Executive Director of Utah's Governor's Office of Energy Development. He is responsible for the implementation of the Governor's Energy Plan, state energy policy, and related legislation to advance responsible energy development. He leads a small technical staff in advancing lasting investment in Utah's energy infrastructure, technology, and workforce. He also develops state comments and strategies to address a variety of energy issues and proposed federal actions. Before joining OED, Rob was the Associate Director of the Utah Technology Outreach and Innovation Energy Program, where he provided legal, policy, and business support for the University of Utah's advanced energy programs, including carbon capture and sequestration. Prior to USTAR, Rob was the Vice President of the Park City Center for Public Policy, where he developed policy programs in energy, healthcare, education, and environmental management, including extensive work on utilizing integrated resource planning to address the carbon intensity of utility generation portfolios. With that, I will turn it over to Rob Simmons.
Great. Thank you so much, Kevin. And I think we may need to just remind everybody to hit their mute buttons. I'm getting some interesting feedback. But good morning, everybody. My name is Rob Simmons. I'm Governor Herbert's Energy Advisor. And I want to formally thank each of you for joining us for the State of Utah's Energy Storage Summer Webinar Series. Utah and the West face unique challenges in integrating a diverse array of energy resources into the power grid. And as we look to the future, energy storage can improve energy reliability and resilience, and it can support the delivery of intermittent solar and wind resources, which the West has a lot of, as well as Utah, as base-loaded anytime resources. Recognizing the value in educating Utah and the region's energy industry leaders, policymakers, and key stakeholders, the Utah Governor's Office of Energy Development has partnered with the United States Department of Energy's Office of Electricity Energy Storage, Sandia National Laboratory, Pacific Northwest National Laboratories, Mustang Prairie Energy, Quanta Technology, and our own University of Utah's Utah Smart Energy Lab to develop this series. And just as a note, we hope that these relationships that we've formed over these past many years and that have come together for this series, that we can keep these relationships going, and that we can really not just discuss the right types of solutions to bring more energy storage into Utah and the West, but how we can actually, practically do it and make sure that we get on timelines and that we make sure that these great ideas that come out of this series are actually implemented. And before I want to continue, I do want to offer special thanks to two very smart energy leaders from my own office, Kevin Brooks, our Energy Analytics Manager, and Alaire Imre, our Special Projects Director, for their fantastic work on bringing this webinar series together. So Utah is consistently recognized for its ability to generate economic opportunities and a high quality of life. And energy is central to Utah's successful formula. Utah was much of its success to a willingness to invest for the long term. And as a note here, I would like to just remind everybody and also tell people about Utah a little bit. Utah is the youngest state in the country, and it's the youngest state by almost 5 years. And so certainly Utah, of all states, wants to plan for the long term. And in energy, if you're going to plan for the long term and create lasting changes for the better, then you have to invest in three things: technology, infrastructure, and workforce development. Utah is located in the heart of the Western Energy Corridor, which means Utah has enormous and diverse traditional and renewable energy resources. And one of the keys to taking full advantage of these energy resources and doing it in the right way with limited emissions is through energy storage. A little historical note, last year Utah celebrated the 150th anniversary of the completion of the nation's first transcontinental railroad here in Utah. You're probably going to ask why I'm pointing out this historical note, but this led to Utah becoming known as the crossroads of the West because we brought together much of the West infrastructure. Utah is also strategically located for energy storage. We have all the great resources and we have all these amazing assets here in Utah and the West to make energy storage a reality. So Utah is strategically investing, establishing itself as the crossroads of the West, as a new crossroads of the West for innovative energy development and storage. Really quickly, I want to talk about the three things that are needed for a successful energy project. Been involved with enough energy projects for enough time that I've recognized that there's three things that you absolutely have to have if you want to have a successful energy project. The project must be technically viable. This is obvious, but the project has to work. The science and all of the technical aspects of the project have to be in place first before you can do anything else. But also, for the project to be successful, it has to be economically viable. And it also has to be politically viable. With the last two, depending on sort of how economically, when you look at how economically successful a project might be, you also have to look at the political viability. And if you have a project that has an amazing potential economically, you can sort of get away with not having as much political support as you'd like, and vice versa. If you have a project that has amazing political support, sometimes you can get away with not having all the economics in place. Nevertheless, like a three-legged stool, if you're going to have a successful project, all three of these things have to be in place. You have to have the technical know-how, it has to be economically viable, and it has to be politically viable. So starting today and meeting every Wednesday morning through August 12th, the State of Utah's Energy Storage Summer Webinar Series will consist of 6 webinars featuring a series of the leading experts in the country and even the world, presenting on the technical, economic, and policy solutions needed to advance large-scale energy storage here in Utah and the West, and really throughout the world. So on behalf of Governor Herbert and the State of Utah, I thank and welcome these remarkable presenters and you to the Energy Storage Webinar Series.
Excellent. Thank you, Rob. So moving on to the introduction to energy storage and Q&A. I would like to introduce Dr. Gyuk. Dr. Gyuk directs the Energy Storage Research Program at the U.S. Department of Energy, which funds work on a wide variety of technologies such as advanced batteries, flywheels, supercapacitors, and compressed air energy storage. Applications include seamless continuity of power supply for high-tech industry during outages, making renewables dispatchable, and helping to increase the capacity factor and ease congested distribution lines. Dr. Gyuk has a bachelor's in science from Fordham University and did his graduate work at Brown University, where he was a research assistant to Nobel laureate Leon Cooper. He has his PhD in theoretical physics from Purdue University and became a research associate at Syracuse. Dr. Gyuk has taught physics, civil engineering, and architecture at the University of Wisconsin and Kuwait University. With that, I will hand it over to Dr. Gyuk.
Hello?
Hello, we can hear you.
Is everybody muted? I can hear an echo. Okay. Hello, and it's nice to be here in Utah, virtually, if not physically. I'm Imre Gyuk, and I direct the Energy Storage Research Program at the Department of Energy, Office of Electricity. And I'm going to give a general introduction to energy storage for resilience, stability, and a greener.
Dr. Gyuk, I think you muted yourself.
Am I here?
Yeah, now we can hear you.
Okay. Well, I'm back again. Energy storage is a simple concept, basically. It provides energy when it is needed, just as transmission provides energy where it is needed. So time and space. Why are we doing energy storage now? Why didn't we do it 20 years ago? Well, there has been a change on the grid itself. It used to be that the grid was deterministic. We had generation and we had load, and the load behaved fairly predictably, and all you have to do is adjust generation, send it through transmission, and you could respond to the load. Well, things have changed very considerably. The grid has now become stochastic. Both generation and load are variable. No longer do we just have fossil fuel generation, but we have wind, solar, and other renewables. And these are variable. The load side is more complex too. We have the load as before, but we are beginning to have electric vehicles that are part of the load. We have rooftop PV, and everybody has a ton of electronics in their house. So we have a variable load and a variable generation, and transmission alone is not enough to link those. We now need storage, which makes the linkage in time. The DOE Office of Electricity has an energy storage program which is devoted to bringing this storage about, to making it a reality. We support a broad range of R&D, of deployment, of analysis, and we do the entire spectrum from materials to devices to systems to analysis, standards, and policy. We team with Sandia, PNL, and Oak Ridge. These are our main labs. And we also work with Argonne and the Los Alamos National Laboratory. And this is to work with industry, states, and utilities. And we get a lot of awards. So this is the outline of our program. At the core, we have materials research, which works on such things as zinc manganese oxide, flow batteries, sodium batteries, and what have you. And we work at the cutting edge of these new types of batteries. We also do power electronics. We work on flow batteries such as vanadium. We are very much concerned with safety issues, and we have reliability, and we now have a new test center that's being developed at Pacific Northwest Laboratories. We are strongly involved in state regulatory support. This webinar series is an example. We evaluate use cases. We develop performance protocols, and we are very much interested in the development of safety codes and standards. So what does it take to actually have a project in energy storage? We need a business case. And the business case depends on both the cost of a storage system and the value of a storage system. And ultimately, these have to be the same. The cost is, of course, the energy storage device itself, but also power electronics and the balance of plant. This is very important. The value of the storage system comes from such things as frequency regulation, arbitrage, demand charges, which come by the month and by the year, and also from unmonetized issues such as resiliency. We have actually become quite good at evaluating the cost and benefit, and there are tools available, such as the one that we developed at Sandia, where you can just put your particular situation into it and out come the answers that will give you an estimate of whether you have a valid business case or not. And this is available for free to anyone. So with the stated values, this is easy. However, with the unmonetized values, this is a little bit more difficult. Values such as resiliency, military energy assurance, and emergency preparedness are difficult to monetize. But often they are actually the primary reason for having a project in the first place. Microgrids, for example, with renewables on them, plus storage, are good solutions for resiliency. Having a microgrid, you can go off-grid, you can be prepared for disasters and various other situations. But the business case itself has to rest in general on monetizable benefit streams. So we are engaged in building and validating business cases on resilience, sustainability, and grid stability. Those are our main interests. And I have some examples here. For example, Sterling, Massachusetts. This is a microgrid storage project, which was originally based on a $1.5 million grant from Massachusetts. We got interested in this because there were 10 such grants. And the trouble is, when the grants go to small towns, they frequently do not have the knowledge, the expertise to proceed with a valuable and useful project. So we got together with one of these municipals, Sterling, Massachusetts, and we told them, look, you had proposed using a megawatt roughly to make your police station and dispatch center independent of the grid so that during disasters the police station could survive and function. Wouldn't you like to make some money in additional and have the whole thing pay for itself? And of course the answer is yes. And so we put the whole data available on the computer at Sandia, and we came up with a business case for Sterling. And the business case showed that by taking advantage of arbitrage, monthly the demand charges on monthly peaks and annual peaks, we could provide a total of about $400,000 a year in payback. And they decided to do it that way. And within 3 months, a storage project was created by NEC. You can see the group of people who were there at the opening. 3 months later, the plant was finished. And then over the next year and a half, savings started to accrue. And as you can see, you have the monthly savings going along in the during the year on monthly demand charges. And then you have a big jump for the yearly demand charges. Then it goes into the monthly demand charges. And after 2.5 years, we had saved Sterling $1 million in avoided costs. And the place has since gotten somewhat famous, and there have been visitors from Germany, Switzerland, Denmark, Sweden, England, etc., etc., etc. So here's another example. Cordova, Alaska. Again, it's a municipal system. Municipal systems are easy to work with because they can reach decisions very fast. It's a beautiful place, but it's completely isolated from the grid. It has its own grid, which depends on hydropower, 6 megawatts run-of-the-river hydropower. Now, run-of-the-river hydropower is not easy to control, and sometimes there's too much and sometimes there is too little. So the hydropower had to be backed up with considerable amounts of diesel, and there was about half a megawatt was deflected as spinning reserve. So what we did is we suggested putting in a megawatt of storage. You can see the ribbon cutting here. This is the unit as it sits there. And this will do frequency regulation, virtually replacing the diesel. Remember, this is the middle. This is somewhere in Alaska where you have to barge in diesel. You can do load following and again make hydro dispatchable, and it's there for emergency supply and resilience. And here's a third project. This one is on Nantucket Island. They are served by an underwater transmission line, and due to a lot of tourists and a lot of use during the summer, it became apparent that these two underwater lines could no longer supply peak power for the island. So the question was, do you put in a new cable or do you have another solution? Well, the other solution, which was proposed by National Grid, together with Tesla batteries, was to put in storage. And Pacific Northwest Laboratory did the analysis. And it turns out that you get considerable more benefits by storage than you get from doing underground cables. So it is worthwhile. You have $110 million in deferral values and $36 million in operational costs by installing this 6 megawatt, 8 hours of storage. Again, the ribbon cutting and the return on investment is very good there. It's 1.55, which is a lot better than many projects can show. So we are engaged in working around the country with a lot of different projects for which we provide the analysis and we help them collect data, and that gets into validating our model. And usually we also provide a certain amount of cost share. So we are working, for example, with the Albuquerque, New Mexico public schools, where we are demonstrating economic resilience benefits for energy storage, which is available to the public schools. And since they have 140 campuses in this school system, if we are able to show this for one campus, we will probably be able to introduce storage in all of them. Again, in New Mexico, we have a project with one of the pueblos to install storage in combination with solar. In Iowa, we are developing a 6 to 8 hour backup for the existing or planned renewables. They need to put in more solar, and they can't do that unless they have storage available. We are working with NRECA and with rural co-ops and military reservations. We work with Vermont Electric Co-op to facilitate transmission of renewables to the south of Vermont. And we are working at a huge project in Puerto Rico where 5 towns have formed a consortium, the Central Mountain, to have create a Central Mountain microgrid with 250 megawatts of PV and hydro and 75 megawatts of storage backup. So all of these are national scope, but they have to be locally relevant as well. What I'm really after, though, is to create the emergence of storage ecologies, regions where storage becomes an acceptable tool for the utilities and for the legislature to use in providing energy for the public, for the community. California, for example, is one of those with a mandate for energy storage, and there we have the benefit of the California Energy Commission and the Public Utility Commissions and utilities that are very much on board with energy storage. New York has the BEST program and, of course, its funding program through NYSERDA. California and New York are probably the biggest funders of energy storage. We have universities such as CCNY. The Northwest, with Washington, Oregon, and Alaska, is another storage ecology with Pacific Northwest Laboratory, with the Washington Clean Energy Fund, very strong, the Public Utility Commissions, and Senate participation in developing storage regulations. New Mexico has Sandia, congressional support, and a lot of projects coming up. Massachusetts, again, a strong state with Doer there, with many projects, with the national grid as a utility, and with many universities that are able to participate in the development, of storage. So in order to have a storage ecology in your region, you need congressional and state support, you need regulatory structure, you need national laboratories or similar organizations, you need universities, utilities, and real projects. So that's sort of what I would like to see in the country. And indeed, states have big plans. California is planning over 1,000 megawatts by 2020, 800 megawatts in the near future. Massachusetts is asking for 200 megawatts by 2020, adding up to 1,000 megawatt hours. New Jersey has big plans by 2021, and New York is planning for 3,000 megawatts by 2030. Arizona, again, by 2030, big plans, and APS, in fact, is trying to put in 850 megawatts in the near future. Even Maine has 300 megawatts planned by 2025, and in Nevada, a single solar farm is predicted at 380 megawatts for 4 hours of storage on federal land. So lots of activity going on, and correspondingly, DOE works with public utility commissions and regular agencies to provide technical assistance through the national labs, Sandia and Pacific Northwest Laboratory. We did a symposium in the Southeast. We did a half-day workshop in New Mexico. We did a one-day workshop in Michigan. Worked with the Arizona Public Service IRP working group, the California Energy Commission working group, with Maine. We did workshops with the PUCs in North Carolina, Rhode Island, and Maryland. The Nevada PUC, a one-day workshop, working on modeling, interconnection, commissioning, and safety. And coming up in the fall, a New England conference of PUCs involving all of the New England states. So as you can see, we are quite active in actually working with the state, something that was actually mentioned in our budget by Congress. As a result, and in parallel, of course, a lot of states are now putting up regulatory structure, and storage is getting into their public policy. Later on, we'll talk more about the policy database, which we are maintaining and which is growing fast, and which is both an agent in helping states develop regulatory structure and in documenting regular structure for vendors and project producers and what have you. So by and large, energy storage has become a resounding success. We are predicting something like $7 million, and it keeps growing, gigawatts annually by 2025. So an exponential increase. But there is a hitch to that. Virtually all of that is going to be lithium ion, so a single technology. And we have some reservations about the incumbent lithium ion technology. There are ecological and sociological issues. Ecological issues in the way it is lithium and cobalt are being mined. Sociological issues because it is not appropriate to mine cobalt in Africa with little boys. We have issues on safety and reliability. There are a number of fires that have occurred with lithium-ion installations, many of them not due to the technology, but due to power electronics and other reasons. And reuse and recycling and disposal are an issue because unlike lead-acid batteries, for example, you cannot simply smelt those and reuse the material. So there are pros and cons. Lithium-ion batteries are low cost, they're market ready, the price is decreasing very considerably, and the vendors are well capitalized. So we know that if you have a lithium-ion project, you will have support for the future, and it's a familiar technology. The con is that the life cycle is less than 20 years, more like 10 years, or shorter than that even. The batteries have capacity fade over their lifetime. They get less and the capacity becomes less and less. There are, as mentioned, safety issues. There is really no appreciable U.S. manufacture, even though in other places many gigafactories are being created. And for me, very important, there is no economical recycling method. All the research is being carried out by Argonne and other places to try and find the solution to the recycling project. And as I mentioned, there are a considerable number of fires that have been registered. Simultaneously, there is a developing urgency. 30 states and 3 territories have now adopted renewable portfolio standards. 7 states and 1 territory have actually set a renewable energy goal. And these are very substantial. They are between 50% and 100% renewable. Well, we all know that the wind blows intermittently and that sun only shines during the daytime. So how are we going to work a 50 or 100% renewable generation economics? It requires longer duration storage. We are no longer going to be content with 1, 2, and 4 hours, which is perfectly fine for smoothing out renewables or providing frequency regulation or other ancillary services. We are going to need 8-hour, 12-hour, day-long storage and even seasonal storage. And what we have to do is we have to look towards earth-abundant elements. We have to look at rock-forming elements or elements, here shown in red, that are used industrially and that are being mined for other purposes in storage and are available in massive quantities. And so DOE carries on materials research on safety, reliability, and recycling, but particularly on developing new technologies using these earth-abundant elements. In fact, we are just developing a huge grid storage launch pad at the Pacific Northwest Laboratory. So what are some of the cost goals for these focused technologies when manufactured at scale? Lithium-ion batteries for the cells or packs, we can look forward to $100 per kilowatt hour. Vanadium flow batteries we have worked on extensively. The price is down to about $300 per kilowatt hour. Among the new technologies, zinc manganese oxide in a 2-electron system could go as low as $50 per kilowatt hour. There's low temperature sodium ion based batteries, maybe $60 per kilowatt hours. And one that appeals to me are aqueous soluble organics for redox flow batteries. The idea there is that the electrolyte will not be based on materials, minerals, but largely on organic compounds. And the price of it will depend largely on how clever science is in synthesizing these materials, and we will no longer have to rely on the stock market. We should also keep in mind advanced lead-acid batteries, which are being improved continually and which are fully recyclable. And those may go as low as $35 per kilowatt hour. And then there are technologies on the horizon for the really long duration. We could, for example, just do better lithium, which is being investigated, which will not contain cobalt, and which will have less degradation as it goes on, and therefore can last longer. But there are also non-lithium technologies, flow batteries, for example, vanadium redox, zinc bromine, zinc manganese, iron chlorine, or materials such as liquid metals being worked with, sodium batteries, such as pioneered by NGK and widely used in Japan. You could do non-battery technologies. The simplest one is just stacking up cement blocks. And the Egyptians did it with the pyramids. We can do it too. Only, of course, we can dismantle the pyramids and get the energy back. Or we can get rail-based systems where we have units on rails that go up and down an incline. The big unit is being produced in Nevada right now. There is a compressed air energy storage. It's a very good technology. We understand it. Unfortunately, there are only 2 of them in the world. I am fairly sure we will see more in the future. Thermal energy systems could be using water and ice, of course, or phase change materials, or more sophisticated systems like Estes and Malta, or systems using liquid air. Another option is vehicle to grid. There will be vast amounts of batteries available in vehicles. And while I do not believe that individual battery charged vehicles are going to be used that way, fleets are certainly available, such as the school bus fleet, postal fleet, and military fleets. There are proposals using frozen electrolytes. What you would do is you would charge a system, you would then cool it down, freeze the electrolytes, maintain the charge indefinitely so there's no degradation, and then by warming up the system slightly, you would make the charges available again. And of course, there is chemical storage such as hydrogen and ammonia. The problem there is that you lose an awful lot of energy in the transformation of power to the chemical and then back to power. And of course, any of these systems can be hybridized together to reach this long duration storage. One of the players to watch in the field is the DOE Grant Challenge, which will be co-led by the Office of Electricity and the Renewables Office at DOE. The big question for all of these technologies, what will be the business case? Ultimately, you have to justify it some way. So are we going to justify it by mandates? Are we going to have massive tax rebates? Who knows? The subject is being worked on very actively because that is what we will see in the future. just a few things for your future use. We are organizing regular webinars in collaboration with the Clean Energy States Alliance, which are available for free. It's called the Energy Storage Technology Advancement Partnership. We also do joint projects with them, with the states. Another thing is the DOE International Energy Storage Database, which has some 2,000 energy storage projects documented, and you can look up technology if you're interested in developing a new project or in just finding out what projects are available. These are all available on our website for free. Well, in conclusion, new technologies are being developed, and with these new technologies, costs will indeed go down, and safety and reliability of storage will increase. But with every successful storage project that's being put on a line, the value propositions will become clearer and they will continue to increase. And simultaneously, more jobs will be created in the field. Energy storage should be in the toolbox of every utility, and every state should support it with regulation. Thank you.
And thank you, Dr. Gyuk. Well, we will move on to our next speaker, Dr. Howard Passell, with an energy storage systems overview. Dr. Passell works in the Energy Storage Systems Department at Sandia National Laboratories in Albuquerque, New Mexico. His work focuses on energy storage, grid modernization, energy security, and decarbonization. Over 23 years at Sandia, he has worked on energy and water resource monitoring, modeling management, capacity building, and policy-related projects at various scales in the United States, Central Asia, the Middle East, and North Africa. This included helping to lead Sandia's efforts in the Department of Energy's Solar America Cities initiative and developing energy conservation software and methodology for large institutions. He has worked on emerging national security issues associated with energy, water, food, ecosystems, and populations, with an emphasis on the relationships between resource scarcity and human security. He earned his master's and doctoral degrees in conservation biology and hydrogeoecology at the University of New Mexico. His undergraduate studies were in classical literature and the liberal arts at St. John's College in Santa Fe, New Mexico, and the Ohio State University in Columbus, Ohio. And with that, I will turn the floor over to Dr. Passell.
That group has been a really nice group to work with, very cordial and friendly and professional. And so I thank all of you guys for helping put together such a great program. So I am going to try to provide a sweeping overview of energy storage. And some of this will be a little bit redundant relative to what Dr. Gyuk said. I'll try not to labor those points, but here goes. So let me say a word about this program that is making all of this possible. Thanks to Dr. Gyuk and his program, we are doing outreach to regulators across the country. We've been doing this very seriously for a couple of years. We've done this with well over a dozen states, some individually, some in groups. For a while, we were doing these in person, going to Nevada, say, or to California, and holding workshops in rooms full of people. But then, post-COVID, we've learned to do this via webinar. And in a way, it's better because we can reach more people much more cheaply, burn a lot less carbon, and there are some downsides, but it's working out really well so far. And I hope you will agree by the time this series is over. So let me say a few words to put energy storage in this context. Dr. Gyuk mentioned some of these things. The energy transition is happening now. When I look at that phrase, the energy transition, I think to myself, geez, a few years ago, I'd never even heard of it. And now it's plainly happening in real time. And there's this quote from Buckminster Fuller that I have always remembered from the first time I read it way back when. And it's right there on the screen. If you're in a shipwreck and a piano top came floating by, you might grab it and use it as a life preserver. But if you were in the business of creating life preservers, you wouldn't build them in the shape of a piano top. And I think that's, and his point, and what seems true to me, is that that's what we humans have done over and over and over again. We grasp at some technology that meets an immediate need, and then we hang on to that technology for a long time, sometimes maybe too long. And fossil fuels is a pretty good example of that. It certainly served some important needs, and now we see that some of the unintended consequences are deleterious. And that's one of the things that's driving this energy transition, but there are all kinds of other things: declining costs for renewables, public health issues associated with air pollution and water pollution, geopolitics, where's the oil, where isn't the oil, ecosystem health. So there's a lot of drivers, but this energy transition is happening now, and we are all part of it, whether we want to be or not. It's a wave, and so it will behoove us all to really get on the wave as quickly and as effectively as we can. Now, this is all happening at a time when energy dynamics are completely different. Dr. Gyuk mentioned some of this. Demand, for the first time ever in the history of the United States, and probably, well, in other parts of the world, demand is flat. It used to be the business model for utilities was build more generation to meet increasing demand, but that's just not the case anymore in the United States. So that's a major shift in the way market forces are occurring. Decarbonization, electrification, again, terms that weren't common a few years ago, which are very, very common now. Coal is on its way out. This is not a political issue. This is just plain economics and ecological issues. It's just not going to make a rebound. I can't imagine. PV and storage is supplanting old and new gas peakers. When I first put this slide together about a year ago, that was still somewhat arguable. There were fewer examples. Now it's just a plain fact that PV and storage around the country, people are building PV and storage installations instead of building new gas peakers, and they're retiring old gas peaking plants for in favor of PV and storage. Wholesale and retail markets are shifting on account of all of these dynamics, and the 100-year-old electricity business model just doesn't apply anymore. And one of the things that's important about this, in my view, is that regulatory commissions that have evolved over time evolved along with the evolving electricity industry and energy industry, and that was all pretty linear for 100 years or so, and now it's just gone completely nonlinear, but the regulatory commissions are not being rebuilt, revamped, reimagined. This is not a criticism of the commissions. It's just that the states aren't increasing the commissions and their range and their expertise and the numbers of engineers and others on the staffs and keeping up with these vast challenges. So it seems to me in my interaction with commissions around the country that they're generally understaffed, underfunded, and having a hard time keeping up with all of the challenges. The regulatory commissions are at the hub of all of these changes that are taking place. And so it's really important to bring them along as fast as possible. And that's one of the reasons this program that Dr. Gyuk has initiated, I think, is so important. So we're holding these workshops mostly for the benefit of the regulatory commissions, but also for the benefit of all the entities that exist around the regulatory commissions. And so I think that's pretty much the case with this Utah series. So along with the energy dynamics being different, energy storage is different. It's both a load and a generation source. So over the last 100 years, we've had these two things, energy generation, energy load, and now we've got this third thing, and we don't quite know where to put it. We're trying to lump it in between, and it's an awkward marriage. And so we would be better off to rethink that. Energy storage allows for demand management. As Dr. Gyuk said, it defers new generation and transmission, so there's a lot of money to be saved by putting in a battery instead of putting in a new transmission line, say, or new generation sources. We know that it unleashes the power of renewables. It provides various services and value streams, and it provides flexibility, resilience, and reliability. And I'm just breezing through that because Dr. Gyuk has already mentioned a bunch of those things. Oops, gone the wrong way. We don't want to go that way. Okay, so a lot of the rest of this presentation is going to be on the technical side, and so I want to talk about some of the terms that just keep coming up over and over whenever you're talking about these subjects. I'm assuming I'm talking to an audience of mostly generalists. I'm not an electrical engineer myself. I had to learn all this stuff. I'm an ecologist, as Kevin said, and I came into energy storage a few years ago, and a lot of this stuff is stuff that I had to learn, so I have beginner's mind when it comes to some of these topics. So I hope that this is useful to you. What's a watt? Well, it's a joule per second. A joule is a very tiny little bit of energy. It's 1 calorie, which is the energy required to raise a gram of water from 1 degree C, which I think is actually from 14 degrees C to 15 degrees C, so it's very specific. 4 joules, about 4 joules equals 1 calorie. I've heard it said that the energy released by a wooden match burning is about, I don't know, about a joule, about a calorie, something like that. Anyway, it's a very small amount of energy, but it's important to note that it's got a time function to it, a time term. So a watt is a joule per second. So 1,000 watts or a kilowatt is 1,000 joules per second. A kilowatt hour is 1,000 joules per second per hour. So I have found it useful to try to keep that in mind. We've got two terms that come up over and over again, energy and power, and they're different. So energy is what I just mentioned, a kilowatt hour, 1,000 watts per second for an hour. So that's a measure of capacity over time. It's actually got 2 time terms associated with it. And then a kilowatt or a megawatt or a terawatt, that's maximum generation capacity from a generator. So for instance, I've got this 6 kilowatt PV system here at my house, and that means at the optimal moment of the day when the sun is shining directly on them and the panels aren't too hot and everything is perfect, it's producing approximately 6 kilowatts of energy. And of course, doesn't do that all day long. As the sun comes up, it creeps towards 6 kilowatts, and then as the sun's going down, it creeps away from 6 kilowatts. And so over the course of a day, I accumulate about 28, 29, 30 kilowatt hours of electricity. So it's, increasing and decreasing as the day goes by. You'll see over and over, Dr. Gyuk mentioned some of these things, and these are things that you have to keep an eye on when you're trying to understand the capacity or the function of a battery. A 40 watt, you'll see batteries referred to in lots of different ways. Sometimes they'll just talk about its duration. They'll talk about a 2-hour battery, a 4-hour battery. Sometimes a 40 megawatt 4-hour battery. You got to be able to keep track of what that means, and so on. So you'll have this presentation, and you can refer back to it if you want to. I won't labor some of these points. Generally, energy applications are applications that occur over longer periods of time, and power applications are those that occur over shorter periods of time. So, for instance, frequency regulation, maintaining the proper frequency in the grid, in the transmission system, is a power application. That's short-term injections of power into the grid, and that's actually where most people are making the most money in terms of their energy storage systems. And then on the energy application side, something like arbitrage, where you buy and sell, buy low, sell high, or smoothing the intermittent curve of energy production from PV or wind. Those are energy applications. So, and next week there will be a couple presentations that will dig more deeply into some of these topics. Okay, so continuing, costs are very complicated to track because everybody uses different metrics, and you'll see, as Dr. Gyuk showed, and I'll show in a minute, dollars per kilowatt hour or per megawatt hour, but those often come in for different units. So it could be for cells, it could be for packs, it could be for systems, it could be for the entire installation, and so that really matters. There's a cell on the right, that green thing, the Tesla 18650 cell, but then you put the cell into a pack of many cells, then you put that pack into a system that's got power electronics and other things, then you put it in a building that's got air conditioning and fire suppression systems, and you can have a factor of 5. So the cost of a cell might be multiplied by a factor of 5 in order to get the entire system cost. And when you see those costs, you have to keep that in mind. Capacity, we talked about. Duration, we talked about. Cycles and depth of discharge is a big deal. Cycles, of course, is the number of times that a storage device can be charged or discharged, but that depends a lot on how deeply you're discharging the battery. So a battery that's discharged in a very shallow way will last longer, all else being equal, than a battery being discharged deeply. And depending on what you want to use your battery for, that will dictate what kind of battery you build, what kind of duration, what kind of cycle life, and so on. So I think one of the problems that have been identified in this early stage of battery development is that people put batteries in and they're not so sure how they're going to get their investment back. They're not exactly sure what the battery, how best the battery can serve, and so they're putting in batteries that don't always end up meeting all of their needs. So it's important when you're designing your battery project that you know exactly what you want your battery project to do. Parasitic loads, when you're talking about prices, are often things that aren't included. So in other words, when you build if you have a dollar per kilowatt hour cost for a system, say, or even an installation, sometimes manufacturers won't include the cost of the energy for air conditioning the installation, air conditioning the storage unit that's holding all the batteries, or the personnel, or the land, or the permitting. So there's lots of costs that go along with it that often are not included when you're looking at the sticker price on a project. Energy density is something we'll talk more about, and it's very important. It's the ratio of energy from the battery to the battery mass, and that's important because if you're building a car battery, you need a very high density battery. That is a battery that's small and relatively light, but holds a lot of energy. And and if you're putting a battery on the ground in a stationary setting, in a storage unit, grid scale, or in someone's home, in the garage, or elsewhere, it can be a bigger, heavier battery because the size and weight aren't quite so important. So that's something to consider. And then round trip efficiency, how much is lost? Every time you fill a battery and drain a battery, you're going to lose some energy in the process. Friction is everywhere. And so how much of that is lost is a very important thing to consider. As Dr. Gyuk showed, battery deployments are just going up exponentially around the country. However, grid-scale battery storage is still less than 0.1% of generation. So in other words, we're generating way more than we're storing. We could be storing much, much more of that generation. Not that we would want to be able to store 100%. I don't even know what that sweet spot would be in terms of storage of generated electricity, but we're not nowhere close to that. And also interesting to note, electric vehicles still less than 1% of vehicles sold in the United States, and that's expected to skyrocket. And so, you know, as I was talking about the changes occurring in the grid and in electrical generation and distribution, that's a really important part of that. As EVs increase in the market, then everything is going to change. The load profile will change from daytime to nighttime. And, you know, as electrification takes place, as we put heat pump technology into homes and industries, the load profiles can change. The heating in the wintertime can take over the electrical load profile. So there's just huge changes coming, and batteries are going to be a really big part of that. This is an old number here, 899 megawatts of grid-scale storage by 2019. We're already exceeding that and looking at much, much bigger projects coming up down the road. Here's a picture of how prices have declined out to about 2019. You can see the declines were steeper early on. And by the way, so just to be consistent here, this is the battery pack price. And here's the pack right here. Here's a picture of a pack. So the battery, that's on the right. I'm assuming you guys can see my cursor. If you can't, somebody let me know. But anyway, the battery pack price is declining more rapidly at the beginning, and it's starting to flatten out now in the last couple of years. And most analysts think that the savings in the future are going to come from the system, the whole system, rather than in the cells. Although, as Dr. Gyuk pointed out, there are a lot of battery chemistries which are being experimented with, which could keep bringing these costs down. Lithium ion is the elephant in the room. There's a few other technologies. Lead acid, sodium sulfur, flow batteries. One of the differences between the different technologies or chemistries is the average duration of the discharge, and so lithium ion is shorter period, flow batteries a little bit longer, sodium sulfur, and so on. So those are some of the different selling points of the different technologies. And I'm going to go over some of these technologies in a minute. Let's just look at the graph on the left, power capacity. This shows us a couple things that are interesting to note. The blue bar is PJM. That's the market, the power market on the East Coast, many of the Northeast Coast cities and states. And you can see that most of the installed capacity is in PJM. That brown bar next to it is California, CalISO, the independent system operator in California. And if you look just below that, you see frequency regulation is getting the lion's share of the revenue for PJM and for California too. And then as you go down that list, you see many of the other ways that utilities and other third parties are making money off of energy storage. But so far, they're a small part of that return, and most of it is in frequency regulation. California is making a lot of money off a lot of different uses. And so you can get a sense from this about how these things are being employed. And there'll be more about this next week. As we've been talking, as the size goes up, the duration goes up, the costs go down. It's noteworthy that in 2008, a 1 megawatt, 15-minute battery at PJM for frequency regulation was a big battery. This is a graph that I got from the Energy Storage Association, which is the the Trade Association for Energy Storage. This is less than a year old, and this graph shows a 300 megawatt battery slated for installation in 2020. Well, it's already old. Nevada has a 350 megawatt battery. California's got 1,000 megawatts on in being planned over multiple batteries. So things are changing really, really fast in this battery technology business. So let me go over the broad range of energy storage technologies. Batteries are not the only thing. There's a bunch of others. And it strikes me that it's so interesting right now that lithium ion, a 2 or 3 hour lithium ion battery is the market leader right now. And there's so many other applications for energy storage, especially longer duration storage, which would be really important and really valuable, but we haven't figured that out yet. And there's so many other chemistries that are coming up. Right now, pumped hydro is the lion's share of energy storage in the United States. Something like over 90% of the energy storage in the United States is pumped hydro. This is compressed air energy storage, the red bar, and I'll talk more about both of these technologies. Battery energy storage is a relatively small part of the landscape, and then capacitors and flywheels are smaller yet, but have very specific, address very specific technological demands. So pumped hydro, 95% of U.S. capacity, long duration, high capacity, 70-80% round trip efficiency. That's pretty good. Good batteries, the best battery technologies are up in that range and higher, but that's still a pretty good round trip efficiency. You pump water up into a reservoir, and then when the energy is cheap, and then you let it run back down through the turbines to make electricity when the energy is more expensive or when you need it. There's a lot of these in the East, partly because some parts of the East are mountainous, and you have the terrain that agrees with the technology, but also because of the nuclear power that grew up in the East. And you know, when you're running a nuclear power generator, you want to turn it on and leave it on for months at a time, running at the same level. You don't want to jack it up or lower it. You want it running as base load. And so that often means it might mean you're making more electricity at night than you need. And so they wanted to be able to store some of that and then use it during the day. But one of the biggest problems with pumped hydro is how do you place new ones now? Nobody wants, the environmental impacts of these things are big. It's hard to site them now. It's hard to get all the permissions that you need in order to do it. It's expensive to do. It's low energy density relative to some other technologies. So those are some of the drawbacks. And mostly it's just hard to find places to do it, and hard to find places where you will, get the public to agree that it should be done. Compressed air, another technology very similar. You use electricity when it's cheap or when it's plentiful to compress air, pump it down into geological storage, and then when you want that energy back, you release the compressed air through turbines and create the energy again. Very low round trip efficiency on this, low energy density, long life. And by the way, I want to mention something. All of these technologies could store energy for as long as you want. You could fill a battery with a charge and let it sit until, for 6 months, and then you could let it run out. Same thing with compressed air, same thing with pumped hydro. So when we talk about duration, you could use it as seasonal storage, but the problem is it isn't economical. You can't get your money back if that's the way you're using this installation. And so it doesn't make any sense to invest $100 million into something and then just get a tiny fraction of that back. So the economics drive a lot of the ways that these technologies are used. Flywheels, super fast, high cycle life. broadly applied in lots of different technologies, but limited. Cars, steam engines, potter's wheels. These things are not frictionless, but as close to frictionless as we humans can get one of these machines to be. And they spin. You keep them spinning. You add bits of electricity to keep them spinning at the velocity that you want. And when you need the electricity, you draw it off the flywheel. So great source of technology, very, very old, but very limited uses. Supercapacitors, electrochemical, just like a regular battery, long life, high cycle life, fast discharge, high round trip efficiency, but very limited uses. So they're used in some transportation settings. Not so useful in grid scale, but some folks are hoping to make supercapacitors that can work their way into grid scale applications. Concentrated solar power and thermal energy storage. This is a really interesting technology. This is where you have mirrors reflecting sunlight onto a concentrating device. It drives energy temperatures up to thousands of degrees Fahrenheit, and this graph shows that these are old data from a few years ago. All the large scale grid scale battery storage in the United States totaled about 740 megawatts back when this graph was put together. This one plant, Crescent Dunes CSP plant, all alone had the capacity to produce more energy than all the batteries put together. But it's important to note that installation isn't working. It's broken. They can't quite make it do what it's supposed to do, so they're still working on it. There's another plant. I honestly don't know what the status of this plant is. So again, it's a really useful technology. It's not mature yet, but as the need for energy storage increases, as it's doing now, we're going to start finding all kinds of new technologies that start to meet some of those needs that we might have. Gravity energy storage, as Dr. Gyuk mentioned, is another one. I'm an ecologist in background, and in about 70 million years ago, at the end of the Cretaceous, there were all of these dinosaurs stomping around, and the mammals were tiny and small and hiding. And I think of, and this is no joke, I think of lithium like the dinosaurs. They're the dominant species now here in this ecosystem. And there's all of these other little technologies around scurrying about in the bushes, trying to survive and stay out of the way of the dinosaurs. And then when the dinosaurs disappeared, and all of these little mammals grew up into big mammals. And something like that is liable to happen with energy storage. Lithium ion could just become a less dominant technology, and some of these other technologies are liable to become much, much more important. And the question is, which ones and how will they become more important? How will they be used? I think that's pretty much, not very clear right now. So let me spend some time going through battery technologies. I am fascinated by batteries in this sense. When I got into energy storage, I was trying to figure out how a battery works, and I kept asking my electrical engineer colleagues, PhD electrical engineers, and their explanations went right over my head until it dawned on me that the redox reaction that's occurring in batteries is exactly the same chemical redox reaction that's occurring in cellular metabolism. So it's no different than collecting sunlight from the sun, storing it in a energy-rich molecule, which is a carbohydrate, and then the body metabolizes the carbohydrate and gets that energy back. And it's the same. It is amazing to me that across the known galaxy, this is basically true. And some of my less excited colleagues just say, "Hey, Howard, that's just chemistry." But still, it's fascinating to me that it occurs across so many different scales, so many different ranges, across biological organisms, and now we have adopted that and put it into batteries. And there's a picture on the bottom right. I want to say a few things about the way a battery actually works physically. You have a cathode, you have an anode, you have electrons moving in one direction when it's discharging and then moving back in the other direction when it's charging. And a battery doesn't run out of energy. It doesn't run out of electricity. What happens is that there are second order, third order, fourth order chemical reactions going on in the battery all the time. And it's those reactions that gum up the battery. Some of these batteries, a lot of the batteries that we are going to talk about now have a separator that goes down between the cathode and the anode. And it's a semi-permeable membrane that allows the electrolyte and allows ions to pass back and forth across the membrane to keep the whole battery balanced electrochemically. And sometimes the membrane gets clogged up with stuff, and also the cathode and the anode can get precipitates on them, that dendrites, things that grow on them, chemical reactions causing the cathode and the anode to get covered up with different materials. It just causes the battery to stop working. And so that's where battery chemistry research is headed. It's into looking for the combinations of metals, the combinations of materials, the chemistries, the electrolyte chemistries that allow you to charge and recharge as many times as you can without losing capacity in the battery, and so on. Lithium ion, as we mentioned, it's the elephant in the room. Here are a bunch of different lithium ion chemistries. There's not just one. Here's a bunch of the different chemistries shown on a graph, and you can see that the one that Tesla uses is the highest energy density battery of them all. Again, why? Because you're putting it in a car. It needs to have a lot of power and a lot of energy and a small mass, a small weight. And that's a description of a bomb too. A lot of energy, a lot of potential energy enclosed in a small object. So that's why these things are dangerous. There's just a lot of energy packed into a small space. And so if suddenly that battery runs away, if it's suddenly released by accident, then it can be problematic. And here's some characteristics of lithium ion. We've already talked about some of them, so I'll skip over this. High efficiency, ubiquitous. It's being used in lots of different places. As Dr. Gyuk said, recycling is still a problem. And here is a picture of how these problems can propagate. So here's the Tesla. On the left is a Tesla battery pack. Here's the cell, the Tesla cell. Over 7,000 cells go into one of the battery packs. And so it's easy to imagine that if one cell fails and catches on fire or has what we call thermal runaway, it can propagate to other cells, and before you know it, there's lots of cells in thermal runaway, and then you have a problem. So just a bit of an explanation for why those fires occur. Another technology that Dr. Gyuk mentioned, sodium sulfur, low volumes or preventing economies of scale. There is one problem, or one of the drawbacks to it is you'd have to keep this hot. This is molten sodium in the middle of the battery. So you have to keep this battery at 300 to 350 degrees C. So you have to put energy into it to get it to work, or you have to keep it hot to get it to work. And so then not only is it using energy in that regard, but it's also this very hot thing that has to be protected or protect other things around it. I have a colleague here who you'll hear from in a couple sessions, Dan Borneo, who puts these systems together. He builds these projects for DOE, for Dr. Gyuk, and what he says about these other technologies is that they just don't work. They're being applied in places so far they have some niche applications, but he just doesn't have faith that they're reliable and that they'll keep working. Lead acid batteries, that's a reliable technology. It has limitations, limited lifetimes, degradation with deep discharge, and various other things. But this is really widely used as you all know, the batteries in your cars are lead acid, batteries in boats. And around the world, people are still using lead acid as storage for PV in various places. I lived in a house back in the 90s that was off the grid, and we had lead acid batteries in the shed that we used to store the energy. Flow batteries, as Dr. Gyuk mentioned, it's an interesting technology. You can see in that picture in the bottom right, you have these two different tanks with different, ones with the anode, one's the cathode. You've got these electrolytes in it. Then you flow these through the fuel cell, and that's where the electrical reaction takes place. And so there's some virtues to this. You can change the output of the system by enlarging or decreasing the size of the tanks that hold, and by increasing the volume, the speed with which these electrolytes are moving through the system. So it can be a more versatile system, but round trip efficiency can be low. It's more expensive, might be safer. It's just some of the characteristics of the flow batteries, which are getting more and more attention, and lots of work going into flow batteries around the world. And as Dr. Gyuk mentioned, zinc manganese oxide, that's the typical primary battery. There's primary batteries which only work once and then you recycle them or throw them away. Then there's secondary batteries which can be recharged. Zinc manganese oxide is this ubiquitous. Both elements are very common in the Earth's crust. There's lots of supply chains for building zinc manganese oxide batteries, primary batteries. And so there's a lot of work going on now into figuring out how to make them into rechargeable batteries. I see that I'm running out of time, so I'm going to speed up a little bit so as not to take time off of Will's presentation. Hydrogen storage, it's a same redox reaction taking place. It's a great technology because you split the water into H2, hydrogen gas, and oxygen, and then you put it in a tank. You can ship it across the country. You can store it as long as you want, and then convert it back into electricity. Now, a couple of slides about battery energy storage systems. So as we've mentioned, the cell itself is just a very small part, but in addition to the cell, you've got to have a battery management system that controls the way the battery is charging or discharging, the inverters that switch the energy from DC to AC, energy management systems, site management systems for the connection to the grid, and then the balance of the plant. So a big utility scale battery is a big installation and a very expensive one. It runs the price of the cost, the price of the whole installation up a lot, something to keep in mind when you're planning your system. And there are lots of other topics that go along with this, and Will's going to bring some of those up. It's the policy that shapes the energy storage landscape. Will talk about some of these things. The economics are a big part of that. Design and commissioning is very important. Safety, decommissioning, end of life, lots of things unresolved. The battery industry is growing so fast and so widely, and there are so many new applications. Things are changing really fast, and it's hard to keep up with it all. But it's a burgeoning field, and it's one that will serve us all really well. Lots and lots of resources are available. You'll have this slide, so if you want to go back and dig into any of these things, you'll be able to do so. Some of the things that Dr. Gyuk mentioned are on this page. There's some other things along the bottom that are useful. Sandia National Labs and Pacific Northwest National Labs and Oak Ridge National Labs and Argonne National Lab all produce reports on all of the topics that we've been discussing. They're generally pretty technical, but they'll help you dig deeply. And I would encourage you to go to some of these sites and see what you can find out. There's a lot of really interesting, useful information at some of these places, and you can learn a lot really fast. So in summary, battery technology is improving, spreading, getting cheaper, getting safer. and it looks, by all accounts, it's going to boom. So good to get on that wave at the front end rather than after it has gone by. We need much more battery capacity with longer durations to meet carbon-free goals across the country. My colleagues here at Sandia have done a study showing that in order for New Mexico to reach its decarbonization goals, which is 100% decarbonized by 2050, we need about 1,000 times, more than 1,000 times more energy storage in the state. Well, so how do you do that? How do you, where do you put it? What kinds of energy storage are we talking about? How do you position it relative to wind and PV? What kinds of new transmission do you need in order to do all that? How will energy demand profiles change over time? What will new EVs do to the system? It's an extremely complicated problem, and so we need methodologies and tools for figuring those things out. There's still lots of things unresolved with regards to energy storage. There is the supply chain toxicity, end of life, and so on. Lithium-ion is the big technology now, but there's a whole lot of other stuff in the background, and people are working really hard to bring those along. As Dr. Gyuk said, batteries provide important services, but valuing some of those is really difficult. Resilience, for example, or community safety, public safety. Those are things that's hard to put a price tag on. And PV and batteries, it's already there. We're already out competing new and existing gas peakers. So the technology, we have the technology. Thanks to Dr. Gyuk for funding these programs and other programs happening around the national laboratories. And please feel free to write to me or call me if you want to talk about any of this stuff. Thanks very much for being part of the series. And with that, I will turn this back over to Kevin.
Thank you, Howard, for providing us with the energy storage systems overview. So moving on to our final speaker, I would like to introduce Will McNamara from Sandia National Laboratories with an energy storage policy overview. Will serves as the Grid Energy Storage Policy Analyst for Sandia National Laboratories with a focus on energy storage policy development at the federal and state levels. Will has spent his entire 23-year career in the energy and utilities industry with a concentration on regulatory and legislative policy. He has served as a lobbyist in California and has represented major utilities across the U.S. in numerous jurisdictions in proceedings pertaining to integrated resource planning, procurement, cost recovery, rate design, and the development of policy-making best practices. Will's area of subject matter expertise, in addition to energy storage policy, include distributed energy resources, AMI, smart grids, renewables, and competitive retail markets. With that, I will turn it over to Will.
Thank you, Kevin, very much. I will pull up my presentation here so that I can share it with everyone. Good morning. Really appreciate this opportunity to speak with you today and begin this, what we hope to be, a very long and productive dialogue with the state of Utah. We really appreciate this opportunity to inform policymakers in your state regarding what we are seeing on a national scale with regard to policy making, best practices, lessons learned. That is the focus of my position here at Sandia. And so I'm going to share with you some of the lessons that I have observed in this role as we've been observing it closely over the last year. First of all, I would like to thank Dr. Gyuk. All of the research that I'm going to be discussing is funded by the Department of Energy Office of Electricity under Dr. Gyuk's sponsorship, so we very much appreciate that. Let's see if I can advance here. What I'm going to cover today is energy storage policy. I'm going to provide an overview into this topic. I'll be mindful of the time and stop at 12:15 Mountain Time so we have plenty of opportunity for questions. So some of this I will go through quickly, but you will have the presentation provided to you so that you can refer to it later. I want to thank Dr. Gyuk and Howard for their presentations. They provide a great segue into the policy discussion. As Howard said, policymaking really sets the landscape. As Dr. Gyuk said, every utility should have energy storage in their toolbox. I agree with that. But I do believe that the extent to which that endeavor is going to be successful for a utility is going to depend on the policy within their region. So today I'm going to go through a historical context of utility industry policy making for those who still may be new to this industry. I'll talk about the distinction between federal and state responsibilities, federal activity to date that's been specific to energy storage, the key energy storage policy issues at the state level, state activities to date, considerations for state regulators, and then a Q&A session. Again, that's a lot to cover in a short amount of time. Here's a list of acronyms that you can refer back to when you're looking at this presentation later. For historical and jurisdictional context, I have spent my entire career in the energy and utility industry. For the better part of the last century, the energy and utility industry was pretty risk averse, slow to change. That all began to change rather dramatically in the 1990s when we, as an industry, started to embark on deregulation or restructuring. That has opened the market to competition and new technologies coming into play. That has created the opportunity for energy storage to become a major participant. But as you can see, dating back to the 70s, policy development has been a consistent catalyst in the energy industry to either move forward renewables, energy efficiency, new technologies, et cetera. Very key to our discussion is what has taken place at the federal level through FERC with orders specific to the wholesale market that are intended to create a level playing field for energy storage. I'll delve into that a bit deeper here. But to be clear, the federal and state responsibilities are very clearly marked. At the federal level, we have FERC, which is the Federal Energy Regulatory Commission. That oversees RTO markets, wholesale markets, the rules governing wholesale practices. Also, rules governing transmission lines are under FERC. Congress is also a party in this, as there can be federal legislation specifically around tax credits that could be applied to energy storage. Right now, we have a tax credit for storage that's combined with solar. At the state level, we have the State Public Utility Commission, state legislatures, and governors who are making policy on energy storage. And this can impact the retail markets, operations of distribution networks, utility rates, and other enabling policies at the state level. So back to FERC, Order 841 is very significant for energy storage. It came out a couple of years ago, and essentially FERC Order 841 has directed the RTOs, the regional transmission organizations across the country, to remove barriers to the participation of electric storage in wholesale markets. Now, not every region has an RTO. Texas, as one example, is not under FERC's jurisdiction, but for the RTOs that do exist, they were required to file with FERC how they are going to change their rules, change their tariffs to ensure that energy storage has a more level playing field. And those plans were all submitted. Preliminary approval has been provided to the PJM and SPP plans. The other plans are still under review, but that, of course, is a very significant milestone at the federal level, trying to remove the barriers for energy storage so that it can participate in the wholesale markets with those services that Howard went through. But in my opinion, the most exciting activity with regard to energy storage policymaking is happening at the state level. It's varying greatly state to state, is really happening in a patchwork fashion. Every state is kind of in a different position in terms of how they're approaching energy storage. The Energy Storage Association puts states into 4 categories when assessing their energy storage policy development. At the really initial stage would be investigating. These are states that are just starting to look into energy storage, conducting energy storage workshops, investigations, getting briefed by various stakeholders. The next level would be clarifying, states that are looking through their legacy rules, whether it's interconnection or net metering or fire and building codes, looking to see how do those legacy policies need to be revised to enable energy storage. Next level up would be states that are energizing. They're really taking some very substantive approaches to energy storage, either through procurement, pilot demonstrations, offering state funding for energy storage projects, or having a mandate for energy storage. And then at the far end, very sophisticated planning states that are incorporating energy storage into their long-term resource planning, valuation efforts, looking at how the distribution system needs to be changed for energy storage. So you can kind of see how a state would fit into one of those 4 categories. Now, as we look at the policy landscape for energy storage, we are primarily concerned about barriers that exist, creating obstacles for the deployment of energy storage. And we're looking to remove those barriers and again create the level playing field. Barriers can fall into multiple categories. There can be just legacy regulatory issues that have been in place for decades. It could be economic issues, it could be utility business model issues, or technology issues. But the policy making that's happening at the state level is really intended to correlate a specific policy with removing a specific barrier, and one of the barriers that would fall into these 4 categories. And a utility commission may find that they have to prioritize certain policy initiatives to remove barriers before they can really focus on enabling policies, let's say. But each policy making typically correlates to one of those barriers. Now, if we start to dive into specific policy issues at the state level, it has been my position, and I have articulated this multiple times in other presentations, but I believe that there are 10 key policy issues at the state level that to one degree or another a state would need to look at. And these, all of these 10 policy issues correlate back to one of the barriers that I just described. So in the amount of time that we have, I will go through the 10 policy issues to give you an introduction into, well, what is the key issue related to this policy issue? What are specific utilities and or states doing within this policy issue? Who's really leading the best practices and providing the lessons learned? Now, any one of these 10 topics, we could spend an entire workshop on. They're very complicated issues. They're very pervasive issues. So what I'm going to do today is just give you the introduction into what the issue is. And then as we continue this series of workshops, I'd be more than happy to delve in deeper and focus on one topic if that's of interest to the audience. But the topics that I have identified are utility ownership, so whether or not a utility has ownership rights to energy storage, multiple use applications, I'll explain what that is, cost-benefit analysis for energy storage, distribution system modeling, procurement mandates, incentive and tax credits at the state level, inclusion of energy storage in utility IRPs, changes to net metering policies, changes to RPS policies, and changes to interconnection standards. So those are the 10. We'll try to get through them all as quickly and efficiently as we can. The first issue is utility ownership. And again, what this issue is that because under historical regulations, perhaps legislative language, typically energy storage has been classified as a generation asset. And within restructured marketplaces that are trying to promote competition, part of that process has usually included requiring utilities to divest of their own generating assets and opening the market to other players. So if there is a prohibition for a utility to own generation, should that be extended to energy storage as well? By default, it would be, and therefore many states are precluding utilities from owning storage. That is a big issue in Texas right now. It's a restructured market, and so within their legislative and regulatory rules, utilities are not allowed to own generation, but there are active court cases with wires utilities, such as AEP Texas, lobbying to have rights to own storage themselves from a reliability perspective. But it's a hotly debated issue. The pros of allowing utilities to own energy storage would be that, well, they would be in a better position for long-range system-wide planning if they were to own the assets. There would be an opportunity to optimize the distribution system because utilities know their own distributions best. There would be an enhanced flexibility to use multiple cost-effective resources. And then as more and more utilities develop energy storage projects, we're going to see the costs come down. So those would be the kind of the standard arguments for promoting utility ownership rights. On the con side, those arguing against it, they would say, well, we have to be very concerned about market power concerns. If a utility could have market power in a particular region. Would utilities have an advantage over third parties? And that would not create a level playing field. Then there are uncertainties about cost recovery and equitable rate treatment among customers. Those kinds of issues have not been figured out yet, and so there's somewhat of a hesitation to allow utilities to own energy storage until those rate implications get resolved. But nevertheless, a number of states have developed policy on ownership, and those are really key points of references. I would direct you to the state of New York. New York operates under a distributed energy resource platform in which, under their policy, utilities really should be neutral about the resources that are providing grid services. And New York does not want their utilities to be in an ownership position for energy storage. There are exceptions to that when a reliability case can be made, but generally speaking, New York is not allowing the utilities to own energy storage. As I mentioned, Texas is another big point of reference. The Texas law clearly defines energy storage as generation, and therefore the T&D utilities cannot own generation, then can't own energy storage. This is working its way through the courts. The PUCT, the Regulatory Commission, said that they were not going to rule on it. They have deferred to the Texas legislature, and we're still waiting on finalization of that. I would also point you to Colorado and Oregon. In Colorado, Xcel Energy's plan has been to replace all of their coal-fired generating plants with utility-owned storage. Now, they're doing that in the absence of a procurement mandate. They're doing that in the absence of kind of any clear directive from the PUC to go out and procure energy storage. But under the model that Xcel Energy is promoting, they would have clear ownership rights and use energy storage to replace all of their coal-fired generating plants. In the Oregon jurisdiction, I think it's important to be watching that because the Oregon PUC has directed the utilities in that state to come back with several proposals for ownership, including outright utility ownership, hybrid ownership, meaning split between a utility and a third party. So there are a whole bunch of different models that Oregon is looking at, and that's kind of providing a lot of real intelligence for the marketplace to be looking at how ownership is going to really manifest in practical applications. So there are four kind of basic models for ownership: the utility-owned, utility split with third-party ownership, third-party ownership exclusively, and then something that we call a virtual power plant model, in which multiple distributed applications of energy storage could be aggregated to provide services to the grid, and those could be either owned by the utility or in a hybrid situation. Some of the key policy questions that surround ownership. Can state regulators ensure that utilities will not gain that market advantage if they have ownership rights? How will the state regulator ensure that third parties can enter the marketplace if utilities are given ownership rights? Will the rate basing of energy storage investments drive down the market value of these services? And then, really, what are the regulatory limitations of a rate-based investment process that would be specific to energy storage? So those are the issues that a state that's wrestling with the ownership issue would likely have to sort through. As I said, going to move through these quickly. I'll be happy to address any specific questions you have going forward. But the next policy issue is multiple use applications. And what this policy issue speaks to is that energy storage has unique characteristics. It can be both load and supply, and therefore it provides multiple opportunities for services that can create multiple revenue streams that may occur simultaneously. And there's a real absence of policy, both at the federal and state levels, regarding how energy storage can participate in both retail markets and wholesale markets, and how that's going to work. Now, the pro of really defining what multiple use applications are would be that it would allow energy storage to fulfill its full economic potential. If we have a very narrow definition of energy storage, that's going to preclude all of the services that it can provide. These composite forms of compensation can combine energy, capacity, environmental, locational, and temporarily specific demand relief. So, there are multiple services that could be explored for energy storage. Now, on the con side, those who would say, we really aren't there yet, we don't know the full scope of services for energy storage, they would argue that right now, most energy storage applications are either behind the meter or grid tied, but not both. So it's kind of theoretical at this point to discuss how energy storage might play in both markets if it's inherently tied to one or the other. The other argument would be that some uses have greater priority than others, such as reliability. So a state may want to take the approach that, well, we're not going to put emphasis on these multiple services. We're really going to focus on how energy storage supports reliability. Now, in terms of best practices, well, let me first kind of be clear on the multiple applications that we're talking about. This is still very much an emerging area for policymaking, but multiple use applications really are it's the umbrella that's trying to capture all of the services energy storage can provide. And as you see in this chart on the screen, there are bulk energy services, ancillary services, T&D services, and then services that are focused on the customer. And the goal for the energy storage advocates is to really ensure that energy storage can provide value across all of these services. Now, as we turn to best practices, California really did emerge as a leader because in 2018, California became the first state to issue revenue stacking rules for energy storage projects. So California defined a set of 11 rules on revenue stacking. They gave direction in terms of dockets and working groups that would compensate for various services that energy storage can provide. So I would point you to California to look at how they approached it and how they defined their 11 rules. In Oregon, Oregon followed California's lead. The state PUC provided guidelines to the regulated utilities, encouraging them to pursue energy storage projects that would stack revenues by being able to perform multiple applications. So the state regulator in Oregon is directing the utilities there to pursue energy storage projects that can provide multiple services, not just reliability. And the services that have been teed up in Oregon would be energy shifting, ancillary services, avoiding renewable curtailments, system peaking, and locational value. And Oregon is presently in that process of looking at the utilities' filings and determining how they want to prioritize multiple use applications. Now, as states look at this issue, some of the policy questions would be, how should those multiple use applications be prioritized? In other words, does system reliability have a greater value than other services, and should it be positioned in that way? How will the multiple values of energy storage be tracked? In California, for instance, resources that are interconnected to the transmission domain are restricted from providing services to distribution domains. So there's kind of a wall between the two that, in California at least, precludes energy storage from providing service to both transmission and distribution. So it will depend on how the state wants to create that framework. But then another policy question would be, can those behind the meter energy storage applications provide grid services? And if so, how should they be priced? So that is something that would fall within a state domain for regulatory policy. Now, the third issue is cost-benefit analysis. And what this policy issue speaks to is that at this point in time, in mid-2020, we are still lacking a clear and comprehensive point of reference for cost-benefit analysis that is specific to energy storage. There's a lot of piecemeal analysis that is available. In other words, there have been cost-benefit analyses done on a regional basis, but the industry is really still lacking something that's universal and comprehensive. And so the policy issue would be, well, should a state mandate that some party under their jurisdiction do a cost-benefit analysis that would be adopted by the state? I'll talk to you about a couple of states that have taken that route, but before we get into that, the pros and cons. The pros of really pushing for a cost-benefit analysis requirement, one of them would be that, well, cost-effectiveness is one of the key tests that must be met to ensure that energy storage procurement targets are being achieved. Now, procurement targets may be a separate policy issue, but what's key here is that without a very strong handle on the costs and the benefits that can be quantified, utilities really struggle with knowing, where their investments should go. So again, utilities may find themselves in a very hesitant position, not wanting to invest in energy storage until more information is known about these costs and benefits. Certainly those that would push for that requirement would say having more accurate cost and benefit modeling will help both the regulators and the utilities when they get to the point of the utility proposing procurement, proposing some type of cost recovery for an energy storage investment. If there's a cost-benefit framework that everyone is collectively agreed upon, that's going to make those evaluations much easier. Now, on the con side, there would be the argument, well, how can we have a state requirement for a cost-benefit analysis when there's really still no universal approach toward defining these costs and benefits? It may be premature to be making that requirement. Also, assessing the viability of energy storage is a challenge, given that these technologies are in varying states of development. Some are still very immature. So it's difficult to do a cost-benefit analysis when the technologies are still so new. And then there's a wide range of performances, and that can create variances in efficiencies and costs. So, you know, it's very possible that we will have to deal with just regional cost-benefit analyses that, you know, due to regional differences, there may not be something that's comprehensive or universal. But nevertheless, states have pursued this requirement. Minnesota is a good example of that. Legislation in Minnesota directed the state's Department of Commerce to conduct an energy storage cost-benefit analysis specific to the state of Minnesota. However, that analysis is publicly available, and I would encourage you to look at it. It's really helpful to see how a state defined the approach to creating this framework. Some of the key findings from Minnesota's analysis was that solar plus storage is cost-effective today in Minnesota, and standalone storage could become cost-effective by 2025. Minnesota has also concluded that over the next 10 years, storage is going to show increasingly positive cost-benefit ratios as more and more use cases for the technology come about. So again, that's a very important point of reference for Utah to know that if you want to look at what one specific state has done in terms of cost-benefit analysis, Minnesota's the one to go to. Some policy questions. Most cost-benefit analysis for energy storage are based solely on the energy benefits of storage, ignoring many non-energy benefits such as job creation, reduced land use, reduced grid outages. So the encouragement there would be for anyone doing this cost-benefit analysis to really, you know, first of all, know what they're doing and make sure they're capturing all of these categories. Secondly, how can a cost-benefit analysis for energy storage ensure that multiple applications are included? We want to make sure that any framework for cost-benefit analysis really explores the totality of services. And then what external resources would be available for regulators? Are there points of reference that can be used for comparison? And that's something certainly that Sandia can provide now that we are comparing states against each other. I think I'm going to skip over distribution system modeling. It's about 2 minutes after the hour. Again, you're going to have opportunity to review this. Let's talk about policy issue number 5, procurement mandates. This is a pretty big policy topic for energy storage. And the policy issue is essentially whether or not a state should mandate that utilities acquire a specified amount of energy storage. Now, the pros in doing this would be that, well, a mandate will stimulate the market, certainly, because the providers know that there's a guarantee that a market's going to exist. There's typically cost recovery for the utility. If a mandate is put into place, the utility can argue that that can be rate-based. Storage projects are typically in the public's best interest, so therefore, should there be a requirement at the state level? And we have a history here of renewable portfolio standards. So is a mandatory approach for energy storage compatible with that approach that required certain amounts of renewables to be developed? Now, on the con side, those that would argue against a mandate, they would say, well, you know, we still have all these uncertainties about how to determine appropriate procurement levels. How much do we know that we'll need, and how can we be certain that the target that is established is the right target? Mandates may allow for the government to pick winners from the marketplace, so that's a concern. And then there's also the argument that, well, current resource planning is sufficient. In some cases, we have states that are pushing for 100% renewables. That's going to drive energy storage anyway, so we don't need a state mandate. However, 6 states do have mandates, and they have really gotten a lot of attention for this. California was the first one with its mandate of 1,825 megawatts by 2020. That includes both behind the meter and in front of the meter storage. Interestingly, their requirement came out of legislation and regulatory mandates. Other states, I won't read them all, but Massachusetts, New Jersey, New York, Oregon, and Virginia all have mandates for specific procurement amounts for energy storage. Virginia, which was the most recent state, they adopted their requirement earlier in 2020. They happen to have the largest requirement now, 3,100 megawatts by 2035, and that was legislatively adopted. Now, key policy questions for a state looking at procurement mandates. Can procurement mandates be effective if there are other legal or regulatory hurdles that remain unaddressed? What is the best approach for determining the appropriate and realistic procurement levels? Should the mandate be statewide, or should it be utility specific? Should the mandate apply only to investor-owned utilities, or should it be applied to munis and cooperatives as well? And then finally, what steps can be taken to ensure that ratepayers do not incur increased costs for what might be arbitrary procurement levels or face increased costs without any associated benefits flowing to them? We often get asked, well, what state will be next? I've talked about these 3 states for some time. Nevada, Arizona, and Connecticut all have been moving ever closely to a procurement mandate, but have not officially adopted one yet. I think any of those 3 states could be very likely to pursue a mandate. And so we will keep our eye on that. But, it's interesting to me, as Dr. Gyuk said, that market development is occurring even in the absence of a procurement mandate. Arizona being a good example that Dr. Gyuk mentioned. There is energy storage deployment happening driven by the marketplace in Arizona. That state does not have a procurement mandate as of yet. Maine is another example that Dr. Gyuk mentioned. They don't have a mandate, but there's lots of activity being driven by the marketplace. Policy issue on incentives and tax credits. I think in the interest of time, I will skip over that. Inclusion in utility IRPs. I think this is an important one, so I'll go through this. The policy issue is that because traditional IRP models do not really consider the value of energy storage, we are finding that energy storage is often overlooked. And so the policy issue would be whether or not a state should require the utilities under its jurisdiction to include energy storage in its IRP or justify why not. And so the pro argument for this would be that what we're finding is that thermal and electrochemical energy storage is now competitive with natural gas peaker plants in some cases, and really should be considered as an alternative. If there's not a mandate for the state, for the utility to do that, would they give energy storage the consideration that it really deserves without having that requirement? Also, a pro argument would be long-term consideration of energy storage addresses other policy requirements such as renewables or clean energy. It provides certainty around the role that energy storage is going to play going forward. On the con side, those would say, how can you have a requirement when we don't have reliable cost data or the best practices fully understood yet? There's still a lack of tools or protocols for analyzing storage, which makes it difficult for IRP inclusion. If this were to be adopted as a policy, it would likely only apply to vertically integrated utilities that are still responsible for generation resource plans. And so what do you do about the restructured markets? That's not capturing that. And it really does not automatically address the local values and flexibility of storage unless you are requiring those utilities to get down to a very granular level at their distribution networks, determining where energy storage should be placed. But again, as always the case, nevertheless, some states have proceeded with this policy. And the states that are displayed on this slide, Colorado, New Mexico, Indiana, and North Carolina, all have some level of requirement mandating that their utilities explore energy storage and include it in their long-range planning or justify why they have not. So we may continue to see that happen increasingly. The policy questions that regulators would want to consider on this topic would be, well, we need to ensure that storage is included as an eligible technology. At this point in time, the majority of states do not consider storage to be an eligible technology. So that has to be changed before we can really start to focus on how it fits into an IRP. How can utilities and regulators ensure that they have access to energy storage data on cost and performance at this point in time? As I said, there's no universal go-to place to have a comprehensive cost-benefit analysis. So utilities might struggle if they're required to do that IRP process. How can utilities and regulators make sure that they are choosing a resource plan model that really truly will represent the full benefits of energy storage and how the technologies function? You know, there are lots of different IRP models. The point here is, how do we know which one is the best and best suited for energy storage? Really would need to find a model that's going to allow for the sub-hourly and stacked benefits modeling that I have talked about and the other presenters have talked about. Net metering, I will skip over. Net metering is kind of diminishing in terms of new tariffs that are being pursued. So we're not seeing as much impact with net metering. I'd be happy to talk offline about it. RPS mandates, I'll go through this really quickly. As Dr. Gyuk said, we're starting to see these RPS mandates increase in terms of the percentage of energy of renewables that's going to be required. That in turn is going to require more long duration energy storage. So the policy issue here is whether or not an RPS that exists in a state should have an energy storage carve out, or whether or not objectives for energy storage should be addressed separately. The pros are that clearly energy storage helps to integrate these intermittent renewable energy sources. So they are partners in that process and work very well together. So it could make sense that there's an energy storage carve out in an RPS policy. Another pro argument would be that including energy storage would help shift renewable generation to more closely match peak loads. It would help provide generation and load balancing services. It would help to reduce the need for peaking and backup generators on the grid, and potentially reduce customer demand charges. Now, on the con side, those would argue that it's uncertain if regulators need to encourage storage specifically. Again, as I mentioned before, if a state has an aggressive RPS, upwards of 50%, going to 100%, is that going to stimulate energy storage anyway? And we don't need to have a specific carve out for energy storage. Also, RPS policies are very complicated. Some date back to the 1980s for some states. Once an RPS is reopened to consider how energy storage fits in, it just creates a real kind of Pandora's box in terms of opening the process for opponents of renewable energy to step in and perhaps try to diminish the RPS. So, you run that risk if you open up an existing RPS to revise it. But interestingly, we have 6 states that have adopted an RPS of 50% or more. So that does seem to be the trend, as Howard talked about. So as we continue to see these states publicly adopt either 100% renewables or 100% carbon-free scenarios, it's really going to require consideration of how energy storage is going to support those goals. If a state is going to incorporate energy storage into its RPS, there are some key policy considerations. What energy storage technologies would be included? Would it just be batteries, or would compressed air energy storage, flywheels, pumped hydro? Would all of the forms of energy storage be included to gain credit as part of the RPS? Should eligibility for energy storage be based on performance characteristics, such as minimum or maximum capacity, duration that the technology can hold a charge? Also, must energy storage be co-located or integrated with a specific renewables in order to be part of the RPS program? So those are issues too that would have to be considered. Now, I show the time as 12:15, and that is when I said I was going to stop so that we could have plenty of opportunity for questions, not just for me, but for Howard and Dr. Gyuk as well. Let me just kind of skip through this to show you where I would have taken us in this conversation, and then we can follow up as necessary. Interconnection rules, these are legacy rules that really create a lot of barriers for energy storage at the distribution level. And then I was going to walk you through just a kind of a high-level landscape. Approximately 15 states, as of the first quarter of 2020, have some type of substantive best practice policy making for energy storage. So you can see across the category policy issues which states represent the best practices. So if any questions might arise regarding what a particular state is doing, please don't hesitate to contact me. I can certainly educate you on a particular state's experience. The final part of my presentation was to go through a regulatory roadmap, just at a very high level, how a state regulatory commission would approach the topic of energy storage. And I think I will reserve that for perhaps a follow-up presentation that I'll have later in this series. I'll just leave you with the point that the energy storage policy landscape continues to evolve. We monitor it on a daily basis. I have a number of tools that I use to track legislation and regulatory and executive directives. So, we're on top of this in real time. All of our knowledge is captured and provided to the public in our database. The link is provided there. I encourage you to go there to check out what we have. And now I'm going to turn it over to Kevin, and we'll have 15 minutes for Q&A.
All right. Well, thank you, Will, for providing us with the energy storage policy overview. So with the remaining time, we will move on to our questions and answers and discussion section. So I've had a couple questions come in through the chat, so I will start with those. The first question that I have is the Department of Energy and National Laboratories showing preference for storage technologies by selection of development activities and funding for specific technology? And is the field wide open at this point? So it wasn't directed at any one of the speakers today. So Dr. Gyuk or Howard or Will, please jump in.
No, we don't have a bias. We tend not to concentrate our research on lithium ion because lithium ion already has huge amounts of research going on in the academic world and in the industrial world. In terms of applications, many of my projects are in fact lithium ion projects. We are interested in other technologies because we feel that eventually they will be needed, and also diversity in technologies will be needed. But no, we don't have a bias for any particular technology. We do, however, have limitations of funding, and so we have to sometimes select certain areas in preference over others.
Excellent. Thank you, Dr. Gyuk, for answering that question there. Is there, in the audience, is there any other questions about the presentations this morning that you guys have? All right. Well, I actually have a question regarding the energy storage systems overview presentation. And Howard, I was wondering, in terms of the systems that you presented, is there a certain approach to deploying them that is most effective? Is it best a kind of mix of energy storage systems, or is there one particular system that might work better depending on an energy mix?
Well, I would say there's different approaches to solving different problems, but may I pass that on to Dr. Gyuk? I'm sure he can answer this question better than I can.
Yeah. All of the technologies have advantages and disadvantages. The biggest thing at the moment is that lithium ion has vendors that are hugely capitalized. And so in terms of getting insurance for your systems, that makes it easier. But if we're going to move beyond 4 hours, if there are applications beyond 4 hours, and there will be and already are, then we really must go to other technologies.
Excellent. Thank you, Howard. Thank you, Dr. Gyuk, for answering the question. During your answer, actually, a couple of the questions related to my question came through from the audience. And one is, which energy system do you think is going to play the main role in the future? And is it going to be battery storages behind the meters or in front of the meters?
Are we live?
Yes, we are live.
So this is Howard. Once again, I'm sure Dr. Gyuk can answer that question better than me, but I'll mention one thing that we're going to have a talk later on in this series by Rohit Nair, who's going to talk about a project which I think might be in Utah, where they're building maybe a 400-unit residential development where each home is going to have a PV system and a battery. And so this is a huge behind-the-meter project. However, all of these batteries are going to be able to be controlled by a third party. Maybe it's the utility. So this behind-the-meter battery can act like a battery that's in front of the meter. So in other words, it can be managed like a utility scale battery. So it's both a distributed battery system and a aggregated battery system. And so it's crossing the line between, behind the meter and front of the meter. And I think it's an example of how the technology is advancing and can advance so quickly that we aren't even thinking of the ways that this technology is going to be applied in, a few years. So anyway, I think that might address the question a little bit.
Excellent. Well, thank you, Howard, for answering that question. Another question that's come in from the audience is, what is the practicality of running your home off-grid, PV and batteries combination, and leaving out the utilities? And this is in respect to people who live in the city.
Well, look, I'll address that too. I'd always leave these to Dr. Gyuk, but I'm not sure if he's still on or got disconnected or something like that. It's really applicable. There's no reason why you couldn't run your system, your home system, off of PV plus storage. Of course, depending on the PV resource, depending upon whether or not you've got shading issues from other buildings around you, depending upon your load, how much energy you want to use, how big your house is, and then depending on the size of your PV system and the size of your battery system. And so that's where the rub comes in. If you've got a lot of load and you want to have completely uninterrupted service like you have in the grid, then you're going to need a big system and an expensive system. And I actually lived in an off-the-grid PV house quite a few years ago, and we modified our lifestyle in order to adapt to when the sun was shining and when it wasn't. And if it was a cloudy day, we didn't run the clothes washer and so on. So it all depends on how you're willing to adjust to circumstances. But the systems can be built. It's really a question of expense. In my view, but I bet that maybe Dr. Gyuk or others or Will would have other thoughts.
Yeah, again, technically feasible, economically probably marginal for individual homes, but it will require lifestyle changes because you're going to have periods where you will not have enough PV for a week at a time sometimes, which means that you're going to have a very marginal availability of electrical equipment. I mean, you can maybe run a radio and a few other electrical critical elements, but you're not going to be able to run your plasma television and your 24-hour air conditioning and what have you.
Excellent. Thank you, Howard, and thank you, Dr. Gyuk, for answering that question. There was one follow-up question to that question could, I think you addressed some of this, could this be achieved, or could this be the future, or is the future still the utilities?
I'll take that one again. It's interesting. There's a big movement in Australia to ditch the utilities entirely. Now, obviously, the utilities don't like it, but about 50% of the public would like to rely on either individual storage plus renewables or on community microgrids. And they want to get rid of the utilities. There is belief in that in the US as well to some degree, but a much smaller degree. By and large, I think we are going to have the grid with us for a long time, particularly because you can build efficiencies into the grid and you can go in for large-scale renewables. But I do believe that we may see more and more microgrids developing, which sort of allow the grids to become an organic construct where individual parts are viable but interconnected.
Excellent. Well, thank you, Dr. Gyuk. So it looks like we are at our time today. So I would like to go ahead and thank all of our speakers today and thank Dr. Gyuk and the Department of Energy's Office of Electricity Energy Storage Programs for funding the State of Utah Energy Storage Summer Webinar Series. Again, I would like to just acknowledge that this has been presented in partnership with the DOE's Office of Electricity Energy Storage Programs in collaboration with the Utah Governor's Office of Energy Development, Sandia National Laboratories, Pacific Northwest National Laboratories, Mustang Prairie Energy, Quintana Technology, and the University of Utah's Utah Smart Energy Lab. I encourage each of you, if you haven't already, to please register for the next webinar, which will be Wednesday, July 15th from 10 a.m. to 12 p.m. and it will cover the energy storage economics. And the webinars are being recorded and the presentations will be shared at some point after the webinar and series is concluded. So thank you everyone and have a great day.
And stay safe and wear your face masks.